So now we understood that how to get the response encoding and the one hot encoder. So right now we have just converted the gene particular column to basically with respect to either a one hot encoder which is going to create 227 columns, or with respect to your response encoding part which was creating 9 columns with respect to your probabilities. So once we have got that, then the question is that how good is this gene column for my final output, right? Now, what is the way we can actually go and test that? So one nice method is we have already created a random model, and there we have seen that what is my log loss, right? So we know my log loss was, let's say, 2.35. Let's say I do not exactly recall, but it's, let's say, was 2.35. Now, in this case, what we will do, we will create a very simple, maybe logistic regression model, okay? And I'm going to build it assuming that I only do have something called as only one column with us, and that is called as gene, okay? And we are trying to predict from it my classes. So simple model which we're gonna create. And during this process, if my log loss comes out to be lesser, my log loss is going to be come out to be lesser in comparison to your random log loss, then in that case, gene is a good feature. Right? So that will be the way we can say that, okay, since it is performing better than any random model, so definitely gene is going to be an important part for my prediction. So that's what we are going to do. Now, in order to do that, we need to understand a few techniques, like basically we have to work on something called as Laplace smoothing. I will explain you what is this now. So this Laplace smoothing is a very interesting kind of method which you should be aware of. Now, this is the concept which you might be introduced in your machine learning concept in naive base, because that's where it have made more sense, but it's a very generic call. So in naive base, what you do, right? If you recall, you kind of, let's say you have various words, W1, W2, W3, and so on, till, let's say, Wm, and you have your classes. Let's say the classes can be either 0 or 1. So in this case, we used to calculate during your training phase I'm talking about. So used to calculate the probability of W1 given that y is equal to 1, because in training phase I used to know my 1 value, that where is my class 1 for word W1. Similarly, I used to calculate for remaining things as well, and same thing we used to do it even with respect to your y is equal to 0, right? So this is the way we used to work in your naive Bayes theorem. Now, I'm not going into depth of all this, because again, I'm keeping my assumptions here that you know what is naive Bayes, okay? But if you really don't know, do not panic. Please go back and do a revision of this algorithm. Or if you still face any issue, guys, feel free to post your questions on your discussion forum, and I would be more than glad to create a video for it. Okay, so if you really feel, or if you want that I should create some nice video for with a mathematical intuition for Bayes theorem, definitely I will do that. Now, coming back to this, now there is a problem is this is happening in the training phase. Now all this W1, W2 till Wm, what I have is are the words present in my training data. Now if I go back and let's say if I look at my query point, which is my test query point, and let's say by any chance my I have, let's say, in my this part I have this, but I do have a word W dash, okay, which is not a part of my training set. Okay, this is quite possible because English keyword is huge, right? So there is a possibility that in my training data I do have some word, but the same word in the test data, or maybe I have a test data set where I do have word which is not even present in my train data. So I have no idea about this W dash, that how it's gonna behave. What is the probability I need to keep for it? So now the problem is, if I have to, let's say, get the probability that what is the probability that it's going to be 1, given that it belongs to my test queue. Okay, now this test queue is nothing but my y is equal to 1, and this is going to be like w1, w2, till w dash, right? Now there's a problem is, if I break down this probability, as per Bayes theorem, it's going to break down something like this: probability of w1, y given 1, this is going to come from a training set, and it's gonna go on, but in the last I will have probability of w dash y is equal to 1. Now the problem is, I have no idea what to do with this term. Now one way could be, you could say that, oh, how about drop it, how about ignore it, right, and take the remaining term. But if you are dropping it, don't you think it is equivalent to saying that you are equating the value to 1 to it, right? And that is not the case. You are giving the value 1 to it if you are actually going to do that. Now there is another idea what people can say: how about making it 0? But if you make it 0, then the whole multiplication will go 0. So again, that will be a problem. So in order to solve this particular problem, we use something called as Laplace. Now, what is this Laplace smoothing? Or sometimes you will hear this term called as additive smoothing also. So that is also, sometimes people do refer it like that. So now in this case, what we do, so we will say P of W dash means probability of W dash where given that y is equal to 1. This is going to be equivalent to earlier what was happening if I have decided that if I would have gone with the technique that, okay, number of training points, basically that it belongs to y is equal to 1, that was basically 0 because there was no points present in my training part, or divided by total number of values. Let's call this as n1. So in the earlier case, we were deciding it to give the probability 0, which was not working good for us because 0 will multiply with everything and return 0. So in order to solve this problem, what we will do, we will add a alpha term to it. Now alpha will be hyperparameter, okay? So this alpha and alpha k, so you might be using all these hyperparameters a lot in your machine learning. So this k is nothing but your total number of classes, okay? So like in my last example, I have taken y as value 0 or 1. So in this case, my value of k could be 2. So in this case, my value will become alpha n1 plus 2 of alpha, okay, like this. Now typically we take the value of alpha as 1. Generally we do that. So we generally want to keep it a reasonable value, and definitely it is a hyperparameter, so you can always change it and see that where your model is giving you the best output, and you can stop there. That's something is always in your hand. Now let's say I have taken the value of alpha as this and assume that I do have 100 points. So my n1 is 100. So what's going to happen in this case? My alpha value is 1 and my this is 100. So plus 2 into 1. So what I got, 1 divided by 102. Now, if you look at this, this value is definitely not 0, right? This is going to be a small number, but it's not 0. Now, you take another case where, let's say I have gone for alpha value to be 10,000, right? Or some huge number. Now, in that case, if I go back to my same part, so 0 plus 10,000 divided by 100 plus 2 into 10,000, because if you remember the k was 2. So here we will get something like 10,000 divided by 210. So I will get somewhere roughly by 1 by 2, not exactly 1 by 2, but almost 1 by 2. So you can see that if I control this value, it can also help me in kind of controlling my something between bias and variance, right? It's a very interesting part. You can actually play with this and see to this part. So this really helps us in kind of doing it. Now the question is that, are we going to only do this alpha multiplication, basically this alpha part, only with respect to my data which is not present? No, because we can't really filter out all this. So what we do, we do this Laplace smoothing for all my whole data set. So even if my data is present, so let's say I have some probability coming out to be 2 divided by 100. Maybe that's the case. It's not 0, but it's 2. So in that case also I can say alpha plus alpha k. It's not going to make any difference for you. So even if the value is there or not there, doesn't matter. We're going to add this for every term present into my algorithm, and that's what we're going to do. So I hope now you got an idea that when we were doing this response encoding, I was considering that alpha as 1. and then I was passing it. So I was just ensuring that if some place it's not present, then it should not return me some value like 0. So that was the idea. So again, this Laplace smoothing is a very interesting concept. Similarly, there is another thing which we also going to use, called as a collaborated classifier. So let me explain you what is that. Calibrated classifier. So I'm explaining you all this because I'm going to use this while building my model. So this is a very simple concept. Let's say I have an input xi and I'm passing it to my model m, and I got the value yi. Now this yi may not be mandatorily a probability term, right? So it may not be probability. Now, in that case, maybe we need some output in terms of probability. For example, like when your final output is required in terms of log loss. Now, in this case, log loss definitely needs probability. Log loss is a complete concept on probability theory. So now, in this case, what we should do then? So what we do is we build it again with a classifier, which is called as calibrated classifier. It may be a sigmoid function, or it may be any advanced level function like isotonic. Okay, so then it is going to return you the form of y dash. This is going to be probability. So as a thumb rule, you can think of it that whenever you're going to use log loss, it's always a good idea to use calibrated classifier, so that your final output should always be in the probability format. So it's going to help you to convert it to the probability format and use it. The third thing we're going to use is SGD. I believe this everybody is already aware. It's called a stochastic gradient descent. Okay, this is, we use it for optimization purposes and all. So this I hope everybody is clear, right? So so these are things which you need to know for understanding the further machine learning model. And now as a next step, we gonna basically approach the whole problem from these three perspectives a lot.